Hello everyone, this video is the continuation of the beams video 1. So in the last video we just discussed about the shape function equation, where from the previous equation, that is the polynomial equation, v of zeta is equal to alpha naught plus alpha 1 zeta plus alpha 2 zeta square plus alpha 3 zeta cube, where this one I'll be writing in terms of the matrix form. So where I'll be taking out all the constant from the equation in the vector form. It can be written as alpha naught, alpha 1, alpha 2, alpha 3. In short form, I can write it as alpha. And even I told you in the previous video itself, if you are not comfortable with the alphas for this constants, go with a naught, a1, a2 and a3. And if I am taking all these things out, what is left out is 1 zeta, zeta square and zeta cube. And this should be even written in the column wise. In case if you want to write in row wise, in the short form always show it as p of transverse, that you need to write it. So this is called as vector of the polynomial basis function, and this matrix is 1 cross 4 matrix because we have 4 degrees of freedom element and we have 4 unknowns in the form of 4 cross 1 matrix. So here we will be discussing the exact shape function values for each thing. For that we need to first find out what is the values of all the constants what we have got in our linear equations. So first we'll go one by one. Let me start with this one. We know that theta is nothing but dou v by dou x, and in case of the partial equation, if you are going the chain the differential chain relationship, it can be written as even dou v by dou zeta into dou zeta by dou x. Already I know what is zeta, which is nothing but x by a. So if I want to write dou zeta by dou x, means it is 1 by a. So this can be written as theta is equal to 1 by a of dou v by dou zeta. Again in the detailed form, it can be written as 1 by a alpha 1 plus 2 alpha 2 zeta plus 3 alpha cube zeta square. And here you can able to see here, and already we discussed the boundary condition, that is here also once again you can able to see here x is equal to minus a or zeta is equal to minus 1. That is the boundary condition. If I substitute here in this equation, what I will get? So v of minus 1 is equal to v of 1 and dv by dx when theta tends to minus 1, which is nothing but the theta 1. Similarly at node 2, when x is equal to a or zeta equal to 1. So here v of plus 1 is equal to v2 and dv by dx, that is zeta tends to 1, which is nothing but theta 2. So if I am writing like either you can say as a d vector or this vector, that is v1 theta 1 or v2 theta 2, which can be written as, you can able to see here 1 minus 1 1 minus 1 0 1 by a minus 2 by a and 3 by a. You can able to see here 2 and 3 is common in this equation. Everywhere I have written. Similarly here everything will be positive, and in the fourth row we will be getting 0 1 by a 2 by a and 3 by a. You need not to confuse this particular thing. I'll be just converting this into the required form, that's all, and this remains as it is, that is alpha naught, alpha 1, alpha 2 and alpha 3. And here in detail I have shown here, like some students still they may have some doubts. So how I got that v1 theta 1 or v2 theta 2 equations. So just continuation of that one. So theta equal to 1 by a of dou v by dou zeta. So 1 by a is alpha 1 plus 2a2 zeta plus 3 alpha 3 zeta square. So at x is equal to minus a or zeta is equal to minus 1. If you substitute in this equation, that is in this particular equation, what we will get? So here zeta is nothing but minus 1. So v1 of zeta is equal to minus 1, which is equal to alpha naught plus alpha 1, alpha 2 and alpha 3 is the constant I will be writing as it is. So zeta only. So zeta is equal to minus 1 and zeta square. So minus 1 square is plus 1. So plus alpha 2 and zeta cube. So minus 1 cube is minus. So theta, coming to theta. So what I will be getting? Theta, which is nothing but 1 by a. So 1 by a constant I will be getting. Alpha 1, alpha 2, alpha 3, write constant as it is. Zeta value, it is minus 1. So there is no zeta here. So it remains as it is minus. How I am getting minus a? Because zeta is equal to minus 1. So minus 2 alpha 2 plus here zeta square. So minus 1 square is plus 1. So plus 3 alpha cube I will be getting. Similarly at this thing node 2 also, how I will be writing? X is equal to a and zeta is equal to plus 1. So I will be writing in this. So v is equal to v2, that is zeta is equal to plus 1, which is nothing but alpha naught plus alpha 1 plus alpha 2 alpha 3, because zeta equal to 1. So wherever zeta is there, if you substitute in this, you will be getting 1. Similarly coming to theta. So here also zeta will be getting 1. So 1 by a zeta 1 plus 2 alpha 2 plus 3 alpha 3. So if you substitute everything in this particular equation, we will be getting this. I hope this is very clear then how we got this particular step. Next, so the next step is the continuation of this thing. So V1 theta 1, V2 theta 2, in short form it is called as a DE. Here you can able to see here, and this entire matrix, that is 1 minus 1 1 minus 1 0 1 by a minus 2 by a 3 by a 1 1 1 1 0 1 by a 2 by a 3 by a. This whole matrix I will be showing it as P, and the constant I will be showing it as alpha. So ultimately I am looking for this one P. So D is equal to P alpha. If I want to get the alpha, means it is D into P inverse. So P inverse is nothing but 1 by 4 of all these things I will be getting. How I am getting 1 by 4 here? Here I have taken constant as 1 by 4. If I am taking constant as 1 by 4, means what value we supposed to fill inside all the locations. You can able to see here. If I take this 1 by 4 inside, what I will be getting? What I will be getting? So I will be getting 1. I will be getting 1 by 2 by 4. So 1 by 2 I will be getting. So like this I have taken the common value, and you can able to see here, and this is again the short form of these things. So in the previous step we discussed about this particular shape function equation, so which demands V of zeta is equal to P transpose into the natural coordinates into the constant alpha. So which can be written as V is that is the displacement function is equal to shape function into DE. I know what is DE, and even I know what is P inverse and all other things. If I substitute in these things, ultimately I will be getting this particular thing, and in short form I can written as N1 zeta, N2 zeta, N3 zeta and N4 zeta. So this is the shape function value I will be getting. So the shape functions for rotations are functional of natural coordinates and the length of the element, and even the shape function for the displacements are function of natural coordinates. Both are there. So this is the the shape function, which is also called as the Hermite shape functions. So N1 zeta is nothing but 1 by 4 of 2 minus 3 zeta plus zeta cube. N2 of zeta is nothing but a by 4 of 1 minus zeta square plus zeta cube, and N3 of zeta is nothing but 1 by 4 of 2 plus 3 zeta minus zeta cube. N4 of zeta is nothing but a by 4 minus 1 minus zeta plus zeta square plus zeta cube. So this is the equation we supposed to remember for solving any beam problems. Either shape functions may be asked, may not be asked, but we need to remember, because by using this equation only even will be deriving the stiffness matrix equation. So this will be an easy method. If you remember the concept of the previous things, see all these things if you remember, easily you can solve any numerical too, because the complicated part which I personally feel while solving the beam numericals is remembering the right formulas. So if we remember this particular shape function equation, that will make us to find out the stiffness matrix derivation also easier, and even any critical deflection at any point of the beam, if it is asked in the problem also, that also we can able to solve. So this is a very important thing. Try to understand how to derive this one. Do not try to memorize this one. So the next slide, where we will be discussing about the strain calculations. So this is also a part of the beam introduction, because most of the problems while solving, even we will be calculating the strain calculations. So for that, the equation is given as always strain is defined as this symbol, epsilon symbol of xx direction, which is nothing but b into dE. So what is b? So this is the equation we have to remember, which is nothing but minus y ln. And what is the expansion of this one is minus y of L is nothing but dou square by dou x square of n. And if you want to again expand this, it can be written as minus y by a square dou square by dou zeta square n. Again it can be written as minus y by a square n double slot. That also we can say. So n double slot is nothing but n1, n2, n3 and n4, which is nothing but twice the differentiation has done for this one. That is the meaning of this one. So already I know what is the shape functions. So if you differentiate it twice, that is twice, the meaning of this one is differentiating this twice with respect to zeta, we will be getting n1, n2, n3, n4 values as this one, that is 3 by 2 zeta as n1 and a by 2 minus 1 plus 3 zeta as